This video is for Chemistry in the Earth System, Unit 2.3, Electron Representations. Today's first main idea, electron configuration notation.
The last line in the square of each element on the periodic table is the precise description of the electron configuration of the element. These letter symbols refer to the electron orbitals, specially shaped regions where we might find electrons moving around the nucleus. Chemists are mainly concerned with the orbitals of the valence electrons because they determine how atoms bond together and the chemical behavior of the element. There are four important orbital shapes: S, P, D, and F. The s orbital can take a maximum of 2 electrons. The p orbitals can take up to 6 electrons. The d orbitals can take up to 10, and the f orbitals can hold a maximum of 14 electrons. There is a direct connection between how many electrons it takes to completely fill the orbitals at each energy level and the number of elements in that period of the table. Let's look at some examples of how the electron configurations of atoms are written. Hydrogen has only 1 electron in an S-shaped orbital. It is written 1s1. Helium has 2 electrons in an s orbital. It is written 1s2. This is saying in the first energy level, the S-shaped orbital is filled to capacity with 2 electrons. Lithium has atomic number 3 and is in the next period of the table. But look how its electron configuration is written. This is a shorthand that chemists have developed. He says that the electrons in the inner energy level are exactly like the electron configuration of helium. 2s1 is a description of the valence electrons. It is saying that in the second energy level, the S-shaped orbital is half filled with 1 electron. Reading electron configurations takes some practice. Let's read one more. Gold. The inner energy levels have the same configuration as the noble gas xenon, whose symbol is Xe. The valence electrons are the following: 14 electrons in the 4th energy level in f orbitals, 10 electrons in the 5th energy level in d orbitals, and 1 electron in an s orbital in the 6th energy level. It was only when chemists understood the electron configurations of elements that they could understand how atoms interact to make the millions of substances that we find in the universe.
Our second main idea, writing electron configurations.
Orbital spins!
Wolfgang Pauli's the guy who... Wolfgang Pauli! He's the guy who figured out that an orbital can only hold 2 electrons. He also proposed that the 2 electrons in the orbital must have opposite spins. This is called the Pauli exclusion principle.
According to the exclusion principle, named after me, Wolfgang Pauli, each orbital can only hold 2 electrons, and they must have opposite spins.
Take helium as an example. Helium has 2 electrons filling its 1s orbital. One of the electrons in the 1s orbital has what chemists call a positive spin, and the other has a negative spin. When 2 electrons with opposite spins fill an orbital together, we say those electrons are paired.
I do.
I do.
If an orbital has only 1 electron, we call it an unpaired electron.
So lithium, with its 3 electrons, has paired electrons in its 1s orbital and 1 unpaired electron in its 2s orbital. Lithium's paired electrons have opposite spins, 1 positive and 1 negative.
Section B, writing electron configurations.
Orbital diagrams represent electron configurations, or the way electrons are distributed among the atom's orbitals using boxes and half arrows. Now that you know how orbitals fill in order of increasing energy with 2 electrons per orbital, understanding these diagrams will be a piece of cake for you.
Let's start with hydrogen again. The orbital diagram for hydrogen uses just one box labeled 1s with a half arrow pointing up. The half arrow represents hydrogen's 1 electron, which occupies the 1s, or lowest energy orbital. The notation 1s1 also represents hydrogen's electron configuration. 1s is the orbital hydrogen uses, and the superscript 1 tells us that hydrogen has 1 electron in that orbital.
Next, there's helium. Its 2 electrons are both in the 1s orbital. So, its orbital diagram also uses only one box. But helium's 1s box has 2 half arrows, representing its 2 electrons. Notice that the half arrows are pointing in opposite directions, showing the opposite spins of the 2 electrons in the orbital. The notation 1s2 tells us that helium fills the 1s orbital with 2 electrons.
1s2 means there are 2 electrons in the 1s orbital.
Lithium, with its 3 electrons, needs 2 boxes for its orbital diagram. The 1s box is filled with a pair of electrons, and lithium's 3rd electron, the unpaired electron, goes to the 2s box. We describe lithium's electrons with this notation: 1s2, 2s1. Lithium fills the 1s orbital with 2 electrons and uses the 2s orbital for its unpaired electron. Now let's skip to boron, which has 5 electrons.
Boron has paired electrons filling its 1s and 2s orbitals, and its 5th electron goes unpaired to one of the 2p orbitals. So boron's notation is 1s2, 2s2, 2p1.
Next, jump down to sodium with its 11 electrons. Sodium fills the 1s, 2s, and 2p orbitals and sends its 11th electron to the 3s orbital because the 2p orbital is full. Sodium's notation is pretty lengthy since it uses a lot of orbitals. It's 1s2, 2s2, 2p6, 3s1. Even without looking at the orbital diagrams, the notation alone tells us that sodium fills the 1s orbital, the 2s orbital, all 3 of the 2p orbitals, and sends its unpaired electron to the 3s orbital.
Some other basic rules that have already been mentioned but we'll name here apply to electron configuration notation. First, as the atomic number increases, the number of orbitals required for the electrons also increases. Also, all of the orbitals of one type, being S, P, D, or F, within an energy level, 1, 2, 3, etc., must be completely filled before an electron can occupy the next highest orbital. This is known as the off-bow principle. And lastly, Hund's rule states that all the orbitals of the same energy, meaning in the same sublevel, will be filled with 1 electron before any of the orbitals take on a second electron. This rule means that electrons in nitrogen, for example, are placed in each of the 3 p orbitals before any 2 electrons can share an orbital. Our next main idea, using the periodic table.
There are more than 100 known chemical elements in the universe. Every element is different, but scientists have organized them into a chart called the periodic table. This table groups different elements together where they share similar properties. The first periodic table was made by the Russian chemist Dmitry Mendeleev in 1869. As more and more elements have been discovered, the table has been filled out. The table is structured so that the elements are arranged in order of increasing atomic number. Hydrogen, with the atomic number 1, is in the top left. It's then organized to show the similarities between elements. Elements are set out in vertical columns called groups. Those with the same number of electrons in the outer orbital, valence electrons, are put in the same group. Elements in the first column have one valence electron. Elements in the second column have two, and so on. Elements in each column will share similar characteristics. Rows are called periods. They run from left to right. Each element in the same period contains the same number of electron shells. In period 2, all the elements will have 2 shells. In period 5, they will all have 5 shells, and so on. So, the group number tells us the number of electrons in the valence or outer shell. The period tells us the number of shells of electrons. Let's put it to the test. Fluorine is in group 7, meaning it has 7 electrons in its valence shell, and period 2, meaning it has 2 shells of electrons. What about magnesium? It's in group 2 and period 3. So it has 2 electrons in its valence shell and 3 electron shells.
Our next main idea, noble gas notation. The electron configuration of elements that have high atomic numbers, meaning lots of protons, becomes very complex. There is a shortcut for these elements to make their electron configurations easier to write. This method is called noble gas notation. In noble gases, electrons completely fill the orbitals at a particular energy level. For instance, neon's electron configuration is 1s2, 2s2, 2p6. Each of the 4 orbitals in the second energy level contains 2 electrons. Sodium, which has 1 more proton, has the same electron configuration as neon, plus an added electron in the lowest orbital in the third energy level, which is 3s. All of the elements in period 3, in fact, have the same electron configuration as neon in the n is equal to 1 and n is equal to 2 energy levels. Always having to write 1s2, 2s2, 2p6 for these elements would be tiresome. So to simplify notation, the base electron configuration can be shown by writing the symbol for neon, Ne, within squared brackets. The notation describing the electrons in the third energy level is simply added to the base. For example, the noble gas notation for sodium's electron configuration is Ne, within brackets, 3s1. Noble gas notation allows the electron configuration of any element with a large atomic number to be written in shorthand. It is as simple as writing the bracketed atomic symbol of the noble gas, followed by the additional orbitals that are filled. At this point, you should be able to generate a full and complete response to today's essential question. What is the configuration of electrons within an atom?